Okay, so we have, so if the third property to show that it is a subfield. So for a comma b in S with b not equal to 0, we have we have if I take AB inverse raised to power q, which is going to be a raised to power q, a raised to power q, b raised to power minus q, or you can say that it is, and a raised to power q, a raised to power q is a, and b raised to power, so b raised, this you can also write as bq, b inverse q. Okay, so that is going to be b inverse. Okay, so this means what? So this means ab inverse belong to S. So thus, so Fs is a subfield. Our claim is true. So thus F is a, thus S is a subfield of F. But note that this polynomial also splits our S. Note that because every element of S is a root, so the polynomial also splits our S. Note that the polynomial x raised to power q minus x also splits our S. Splits our S because we have seen that it is a field. Splits our S. Since S contains all the roots of this polynomial. Since S contains all the roots, so this means what? But on the other hand, you have assumed that F is the splitting field of this polynomial. Okay, so being the smallest, then it must be contained in. Now since F is the splitting field, F is the splitting field of this polynomial. Splitting field, we assume that this is the splitting field, so we must have F contained in S. But we just seen that S is a subfield of F, so this means S and F, they are same. S and F, they are same. Okay, now since S has Q elements, since S has Q elements, so therefore F also has Q elements. So this means then that F has Q equals to p raised to power n elements. P raised to power n elements. So for every prime p and for every positive integer n, there exists a field with this cardinality, and that is F. Okay, and that field is nothing but the splitting field of the polynomial x raised to power q minus x our fpx. Okay, so the existence part is there. Now see the uniqueness part. Now uniqueness. Okay, so we will first show that every field with this cardinality is actually a splitting field of the polynomial, some polynomial that we claim, and from the uniqueness of the splitting field, the uniqueness would follow. Okay, so let F be a field, finite field with q equal to p raised to power n elements, then by theorem, now see here the theorem that we have proven previously. Just one moment. uh, okay, okay, so I can't show that because that lecture ended, but you remember the theorem, the second theorem that we proved in the in the previous lecture. Then by theorem 2, then by theorem 2, f has characteristic p, f has characteristic p, and so contains fp as a subfield. And so because every field of characteristic p has fp, its a prime subfield, and so contains fp as its subfield. Okay, and by lemma 4, f is a splitting field for this polynomial. By lemma 4, f is a splitting field, splitting field of polynomial, because we have, if we have a field of characteristic p containing fp as its subfield, then we have just seen in lemma 4 that f is a splitting field of the polynomial x raised to power q minus x over fp. Okay, and since the splitting fields are unique, the result now follows by the uniqueness of the splitting fields. So any finite field with q equal to p raised to power n elements turns out to be a splitting field of the polynomial x raised to power q minus x over fp. Okay, and the splitting fields are unique, so therefore the result follows by the uniqueness of splitting fields. The result now follows by the result now follows by uniqueness of splitting fields. Splitting fields. Okay, so we are done. We have shown that for every prime p and for every positive integer n, there exists a unique field with this order. Okay, so as a note you can write then, so you can denote a finite field with this symbol. So thus we can always denote a finite field with fq. Now this is our standard notation now for finite fields, because we have just seen that finite fields are precisely of this form. Okay, and in fact unique. So this is the standard notation for a finite field. So we can always denote a finite field with fq, where q denotes a power of the, where q denotes, or you can say that q equals to p raised to power n, where p is the characteristic of the field, where p is the characteristic of f, where p is the characteristic of f, characteristic of fq. Okay, so this is the characterization of finite fields. Now we will look into the what are the subfields of such fields? Okay, we have just seen that finite fields, they are of this form. So what would be the possible subfields of these fields, finite fields? In fact, we have a criterion for subfield. The next theorem is a subfield criteria for finite fields. So this is a theorem. So a theorem which is a criteria for subfields. Okay. So you call it, this is a theorem 6, and call it subfield criterion. Subfield criterion for finite fields. Okay. So let fq be a finite field. Fq be a finite field with q equal to p raised to power n elements, p raised to power n elements. Then every subfield of fq, then every subfield of fq has order p raised to power m, where m is a positive divisor of n, where m is a positive divisor of n. And conversely, if m is a positive divisor of n, then there is exactly one subfield of fq with p raised to power m elements. Conversely, if m is a positive m is a positive divisor of n, there is exactly then there is exactly one subfield of fq with p raised to power m elements, with p raised to power m number of elements. Okay, so let us see the first, let us see one by one. So see the proof. So first we will prove that if we have a finite field fq with p raised to power n elements, then every subfield of fq has order p raised to power m, where m is a positive divisor of n. Now let k be the subfield of fq. So let k be the subfield of fq. Then k must have p raised to power m elements, where m is less than or equal to n. Okay. Then k has, sorry, then k must have k must have p raised to power m elements where m is less than or equal to n. How? Because of the Lagrange's theorem. Because of the Lagrange's theorem. Because order of k being a field, it is additive group. So order of k must divides order of fq. Okay, because order of k divides order of fq. Okay, so m is less than or equal to n. But by lemma 1, q must be a power of p raised to power m. But by lemma 1, but by lemma 1, q, which is p raised to power n, must be a power of p raised to power m. Must be p raised to power m raised to power k. Okay, so from here you can say that n is equal to mk. So you can say that m is a divisor, positive divisor of n. So m is a positive divisor of n. Conversely, let m be a positive divisor of n. And we show the second part. Conversely, let m be a positive divisor of n. Positive divisor of n. That is, you can say that n is equal to mk, where m is positive. Then this would imply that p raised to power m minus 1 divides p raised to power n minus 1. Okay, and so you can say that the polynomial x raised to power p raised to power m minus 1 divides the polynomial x raised to power p raised to power n minus 1 in fpx. These are just small calculations, you can check this. Okay, so if m divides n, then p raised to power m minus 1 divides p raised to power n minus 1, and it would imply that the polynomial this divides this in fpx. Okay, so from here you can say that every root of the polynomial x raised to power p raised to power m minus x is a root of x raised to power p raised to power n minus x, which is x raised to power q minus x. You just multiply x both sides, you would get from this relationship. Okay, so every root of x power p raised to power m minus x is a root of x raised to power q minus root of x raised to power q minus x. Okay, and roots of x raised to power q minus x are nothing but the elements of the field this fq, because we have seen that this fq is nothing but the splitting field of the polynomial x raised to power q minus x, and hence belongs to fq. Okay, so it follows that this fq contains the splitting field of this polynomial x raised to power p raised to power m minus x. So thus fq contains the splitting field of the polynomial x raised to power p raised to power m minus x, our this field fp. And by theorem 5, just the previous theorem, Such a field, by the theorem that we have just seen in the existence and uniqueness of finite fields, such a field has order p raised to power m. And by previous theorem, such a field must have order p raised to power m. Okay, so if m is a positive divisor of n, then you have a subfield of fq, which is the splitting field of this polynomial and which has order p raised to power m. Okay, and and splitting fields are unique, so therefore that field be that there would be exactly such field. Okay, if there were two distinct subfields of order p raised to power m, they would contain more than p raised to power m roots. Now, since splitting fields are unique, since splitting fields are unique, fields are unique, there is exactly one such field. There is exactly one such field. One such. So we have seen a very important characterization for subfields of a finite field. Okay. So they are precisely of the form, they have precisely the order p raised to power m, where m is a positive divisor of n. Okay, so say for example, now if you want to see the subfields of say for example, if you want to see the subfield of, so if we want to see the subfields of say f2 raised to power 30. Okay, then you just have to list all the positive divisors of 30. Okay, so we just need to list all the positive divisors of 30. Say for example, you have this now, f2 raised to power 30 itself would be a subfield, then f2 raised to power 15 would be a subfield, and then f2 raised to power 10 would be a subfield. Then you can say that f2 raised to power 3 would be a subfield. Okay, so f2 raised to power 2 would also be a subfield, and like one. Okay, so this is how you can find the subfields of finite fields. We have some more results on finite fields, but hopefully inshallah we would see those results maybe in the next class. So this class ends here. So okay, see you in the next class.